Well, good morning. It is 11 o'clock. And here we are reviewing chemistry. If you need it, nobody's typed any questions as far as I can see into the chat yet. So if you do have any numbers that you would like to go over, please let me know. If you don't have any, then this is going to be a really short session. As you may have noticed, can you see, first of all, can you see my screen and can you hear me? Let's go for screen first. Can you see my screen? Oh, we got questions. Yes, yes, yes. Okay, excellent, excellent, excellent. All right, so I have a list of questions here. I'm going to circle those. So we have 4, 10, 11, 21, 10, 11, 21, 23, 27, 32, 23, 27, 32, 35, 43, 43, 60, 62, 64, 65, 60, 62, 64, 65, 70, 75, 70 and 75. Okay, and scrolling down my messages now to see what else we've got. There we go. 3, 8, what electron domains are. Okay, so 3, 8. What's an electron domain? More about KP. 3, more about KP, more about KP. Drawing the Lewis structure for NF3, number 24. Lewis of NF3. Okay. And continuing to scroll through the messages. You guys a narration as we have here. Let's see, 6, 11, 13, 15. 6, 11, 13, 15. 23, 24. 23, 24, 26 to 27. 31, 33, 39. 31, 33, 39. 54, 55, 64, 54, 55, 64, and 70. Don't ever apologize for asking too many questions. It is the best way to learn, and a lot more. Let's see, 15, 16, 19, 20, 15, 16, 19, 20, 25, 27, 32, 33, 25, 27, 32, 33, 34. All right, let's see what else we got here. Scroll down, scroll. Why can I not see the rest of the scroll? Okay, I'm gonna make that huge so I can see everything. Okay, 579. 579. Well, look, we're doing all of atoms in the periodic table. This is awesome. 12. Oh, yeah. 26, 27, 34, 28. Oh, and 28 doesn't have a diagram. I will fix that one for you. Okay, 28 needs a diagram. I have posted a new version of that file that doesn't have the answers on those ones that I had on the screen a wee bit earlier. Let's see, 12, 26, 27, 34, and 28 doesn't have a diagram, 38, 39. 43, 46 to 49, 6, 7, 8, and 9, 51, 1, let's see, 23, 27, 31, 39, 49, 51, 52. And how to do without a calculator. Okay, so calculator 4, 67, 69, and 70. Calculator, calculator, calculator. Okay. All right, and adding on, let's see. 27, 31, 32, 33, 35, 39, 42, 43, 44, 48, 51, 56, 60, 64, 78, 88, 92, 94, and 95, 92, 94, and 95. All right, I think I got them all. So let me minimize this chat again. Oh, that's not my pen, that's my pen, not my stylus. There we go. All right, so if anyone hasn't seen it yet, once you get to the second half of this thing, or close to it, number 109 and all the way up to 120 have answers attached to them, and so do number 190 and 191. I have updated the file on Teams. It's on our general post and it's in the files, just in the general files. And otherwise, if you don't want to download that, you can just cover them up or white them out, and I will be putting a diagram. I will be adding in a diagram for number 28 and putting that in there as well. All right. Well, let's get started and we'll see how far we get. If at any point you feel like you're dying and you just want to not be doing so much, that's totally fine. Where did my participants go? I had 9 people and now I only have 7. Bye, whoever you were. Okay, that's all right. So let's see, 3 and 4. So we want to go now to here and we want to go to here. Okay, to make gold stronger and harder, it is often alloyed with other metals such as copper and silver. Consider 2 alloys, one of gold and copper and one of gold and silver, each with the same mole fraction of gold. If the AuCu alloy is harder than AuAg, which of the following is the best explanation based on the information in the table above? There is no table, so I will put in a table for you, and then we will do that one. Table. Okay. Table. Number 4. Also based upon a, no, it actually has pictures. Okay, that's good. Steel is an alloy consisting of iron with a small amount of carbon. Elemental chromium can be added to make it less likely to rust. Chromium atoms react with oxygen, non-reactive layer, preventing the oxidation of the underlying iron ions. An example of steel chromium alloy contains 15% by mass. Which of the following shows the best particle level view of a surface section and an interior section? The atomic radii are given over to the right. So we have iron and chromium have approximately the same atomic radius. And we want to see, so there is a protective coating of chromium oxide on the outside. So I would expect to see chromium and oxygen on the surface. So let's go through here and see if we see some chromium and oxygen on the surface. And I believe this one looks good for that, but let's just check out the others. Ooh, we also have some down in D. Okay, so our surface is looking like either B or D. And then we have, let's see, steel is an alloy with a small amount of carbon. Now, carbon is a much smaller atom, so it would fit in between. And so I would not expect to actually see oxygen in between unless it's attached to the chromium, because the chromium has reacted with it. So these chromiums, sorry, these oxygens here in the structure are there because we have chromium oxide, whatever variant that is. Okay. And we also have it here and here because of the chromium oxide. But in between, we shouldn't really, we shouldn't really see oxygen in the middle, right? Because chromium is not going to get oxidized in the middle because it's got all the other atoms surrounding it. So it's not going to be that. And then this one, we will see carbon in the middle because it is an alloy, except for this looks like really weird. So, well, I still like B. Let's see, was I right? B, excellent, okay. And I think this carbon is just here because, you know, it's an alloy and there's stuff all over the place. Oh, and that's the center. This is the interior. So that's not really a surface one right there. That's still part of the interior. And please do stop me if you're like, what the heck did that mean? Okay, otherwise I will just keep going. And maybe I can make this chat small and off to the side. There it is, good, okay. Number 5. Which of the following species has the electron configuration shown above? So we have 1s2, 2s2, 2p6, 3s2, 3p6. If we go to our periodic table, oh look, I've written all over this. It is worthwhile going through for yourself. And maybe if I erase all this nonsense, we can do it again. So this right here is our S block. This is our first two are the S block. This over here is our P block. And the stuff in the middle is the D block. The F block is down below those lanthanides and actinides. So if we have something that is 1s2, that means we have filled up 1s1, 1s2, and then we're starting on level 2. So we have 2s2, 2s1, 2s2, and then 2p6, or sorry, 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. So I think that was what we had. Let's just go back and check. Oh, 3s2, 3p6. So that would be the third row. So we would go 3s2. No, sorry, 3s1, 3s2, 3p1, 2, 3, 4, 5, 3p6. So we are looking for either argon or something which is isoelectronic with argon. So let's go back. So we don't have argon in our list. So we are going to be looking for an ion that is isoelectronic, which means it has the same number of electrons as, did I say krypton? Or no, I said argon. Go back and make sure. Argon, yes. So I want something that has either gained electrons to become like argon, and chlorine could gain an electron to look like argon. So chlorine negative and argon are isoelectronic. Sulfur could gain 2 electrons, and it would also have 18 electrons like argon. Or we could have potassium, which has 19 electrons. Normally, it could lose an electron to have 18 like argon, and in losing an electron, it would become K plus. So I think I saw a K plus. Yes. Okay. And anytime you see a P6, okay, you're going to have a noble gas configuration. Noble gas configuration. So you will either have a noble gas or you will have an ion, which is in its most common form, because remember the ions form in order to gain that noble gas configuration. How are we doing? Nobody's saying anything. Okay, number 6. Okay. Mass number. All right. Iodine and tellurium have similar average atomic masses. The sample was believed to be a mixture of I and Te when run through the mass spec, resulting in the data above. All of the following statements are true. So Te forms ions with a 2- charge, and iodine forms ions with a 1- charge. Okay. Te is more abundant than I. Okay. I consists of only one naturally occurring isotope with 74 neutrons, whereas Te has more than one isotope. That's true. Wow. Which one would be the best for concluding that the sample was pure Te? Okay, that's the key point there. We need to conclude that it is pure Te. Okay, so this has nothing to do with ionization energy, so we can get rid of that one immediately. Te forms ions with a -2 charge. No. No. Iodine. We'll look at iodine. This one's confusing for me, I gotta say. Iodine, where are you? Okay, 126.9. and 127.6. 53, 126, 127 minus 53. What's 127 minus 53? 127 minus 53. I would skip this one, by the way, if I were like on the exam. I'd be like, ah, screw that. I'll come back to you later. Okay. What's wrong with my pen? Okay. And that doesn't equal 4. Yes, it does. 12 minus 5 is 7, 74. Okay. 127. Ha. Okay. So if it is true that iodine has only one isotope with 74 neutrons, that equals 127, and we have nothing here at 127. So that would be the basis for concluding that this is pure Te, because we don't have anything at 127. And if iodine is pure at 127 for its mass, then it cannot be that. Excellent. Okay. All right, number 7. Based on periodic trends and the data in the table to the right above, to the right, which of the following are the most probable values for the atomic radius and ionization energy for potassium? So we know something about calcium, and relative to each other, where are calcium and potassium? I'm guessing they're right beside each other. Lo and behold, they are. Calcium has 20 protons, so it will hold onto its outer electrons more strongly than will potassium. Okay, because potassium only has 19 protons pulling on its electrons. All right, so back here. So our ionization energy of calcium should be higher than for potassium because the nuclear charge is greater. And in terms of atomic radius, again, calcium has a larger nuclear charge, so it will pull its electrons more closely than potassium. And so potassium's atomic radius should be larger than calcium. So we want potassium to be larger than calcium, so larger. And we want, let's see, ionization energy to be lower than calcium. So that is going to be B. Okay. All right, number 8. Which of the following correctly identifies which has the first higher ionization energy, chlorine or argon, and supplies the best justification? Okay, I'm immediately going to eliminate electronegativity because that has to do with the pull on bonding electrons. And when we're talking about ionization energy, we're talking about removing an electron from a gaseous neutral atom, which is not bonded, obviously. So that one's gone. Higher electron affinity, that's to do with the energy that's released. That wouldn't be a cause. It's another effect. Ionization energy is going to be an effect of a combination of the effective nuclear charge and the radius. When it comes to any of these trends, it's always going to be either mainly due to effective nuclear charge or mainly due to the radius. You can't explain one nuclear trend by saying, well, this one does this, and so that one also does that. That makes no sense. Also, this business of having a completely filled valence shell and that being ultra stable, that is something that we tell you guys all through the junior grades and probably even in grade 11, but it's not actually the reason for anything. So don't give a completely filled or a partially filled shell as an explanation. It's going to be because argon has the higher effective nuclear charge. Remember, you always want to argue in terms of effective nuclear charge or radius. And if you have a higher effective nuclear charge, it will be harder to remove an electron from the neutral atom. Let's just make sure it does have a higher effective nuclear charge. Argon should be to the right of chlorine. I know I've done this for years, I should know that. Yes, there it is. Argon is to the right of chlorine. So it's got 18 protons pulling in as opposed to chlorine, which only has 17. And they also have the same number of shells. So there we are. Okay. Number. Come along. Back to where we go. There we are. That was number 8. And 8 should be D. That's good. Okay. Oh, look, we have a photoelectron spectroscopy thing here. Good, good, good. The photoelectron spectra, a 1s electron from nitrogen. Okay, so we're removing a 1s from nitrogen and from oxygen. Which of the following best accounts for the peak in the upper spectrum being to the right of the peak in the lower spectrum? So we want to know why this one is further to the right. Now, what does it mean to be further to the right? It means that this has that binding energy, which is really related, binding, is lower if it's further to the right, which is sort of counterintuitive, but that's how they do photoelectron spectroscopy. The bigger numbers are over here on the left, and the smaller numbers are over here on the right. Smaller. I think the reason that they do that is that if you think you can kind of make an analogy, if you say, oh, here's my nucleus here, yes, something that is closer to the nucleus, yes, this is my nucleus here, something that is closer to the nucleus is going to be more, it's going to be more highly attracted to the nucleus. The force holding it there is going to be stronger. Okay, so if we think of this as the radius here, that's going to be a smaller distance. And of course, the electrical force, the Coulombic attraction, is proportional to Q1 times Q2 over R squared. So, oh, and I think I've gotten my argument backwards, but that's okay. That's all right. So, why is this radius smaller than that radius? And it has to do with the fact that oxygen probably has a larger nuclear charge, I'm guessing. Let's go look. Yep, oxygen has a +8 nuclear charge, nitrogen has a +7 nuclear charge. So we can say then that oxygen, which has a +8, is more tightly bound than the +7. Then the +7 holds the nitrogens. This is its 1s electron. So ignore anything about half-filled shells. That is a bogus argument. More electron repulsion. If that was the case, if you had more electron repulsion, it would actually be easier to remove oxygen's 1s electron. But that's not the case here. We see that it requires more energy, right? Like 550 or something like that, as opposed to like about 400 for the nitrogen. Electrons in the p subshell of oxygen atoms provide more shielding than electrons in the p subshell of nitrogen atoms. I don't even know what they're talking about there, so just ignore that. And nitrogen atoms have a smaller nuclear charge than oxygen atoms. Once again, we go back to argue in terms of effective nuclear charge and radius. Okay. Number 9. That was number 9. Ha. Number 10. First ionization energy and atomic radius. So ionization energy and atomic radius are going to depend upon the effective nuclear charge. And yeah, the effective nuclear charge and the number of shells. And I think all of these are in row number 2. So this is period 2. So they all have the same number of shells, so we can eliminate a shell argument. So let's see. Which of the explains the deviation of the first ionization of energy from the overall trend? Ooh, deviation, I like that one. Deviation of the first ionization energy of oxygen from the overall trend. So the overall trend is upward. Okay, overall trend is upward. Up, 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 up. And then we go, this is up, up, up. And then we go down. I don't know what I'm drawing. Anyway, if we were to graph it, it would look like this. Boron, carbon, nitrogen, oxygen, fluorine, neon. So that is, why is oxygen smaller than nitrogen, which is the weird one. Okay. So this one we're going to look at our little box diagram. So we have, let's see, 2s, that is, let's see, boron is going to look like this, or 2p, here we go. So here would be boron, and then we have carbon, and then we have nitrogen. Okay, so this is nitrogen, where we have 2s2, 2p, 3. Okay, now you'll notice none of the electrons are paired up in the p orbitals. What happens when we get to oxygen instead is in our 2p subshell, we are going to have, instead we will have 1, 2, 3, and our extra electron there, the one that is going to be moved. Okay, so I'm circling the one that would be removed. It doesn't matter in nitrogen, they're all, oh, what's the word? It starts with a D. That means they all have the same energy. Can't remember, but they all have the same energy. Does anyone remember the word? Meaning they all have the same energy. They are it'll come to me. Okay. At any rate, this electron, degenerate. All these 3 electrons are degenerate. They have same binding energy. Whereas an electron in this orbital here is going to have less binding energy because of the electron-electron repulsion within the single p 2p orbital. So the electron repulsion of the paired electrons lowers the binding energy. Okay, so if we go back, which one says that? There is repulsion between the paired electrons in oxygen's 2p orbital. There we go. Number 10C. Excellent. Okay, number 11. Ooh, photoelectron spectroscopy again. Okay. The portion of the spectrum showing the 1s peaks for atoms, so these are 1s for 2 elements, which of the following for C and F, okay, correctly identifies the 1s peak for F atoms and provides an appropriate explanation? Okay, so carbon and fluorine are both in the same period, but carbon has 6 protons and fluorine has 9 protons. So what we've got is we've got our carbon atom, and it's got I'm only going to draw its outer shell. It's got 4 electrons, 1, 2, 3, 4. And we have fluorine, which has 9 protons. And it has 7 electrons, 1, 2, 3, 4, 5, 6, 7. So, oh, we're looking at the 1s though. So that's going to be the one that's just inside here. So that's going to be here and here. Okay, and they should both have, God, horrible drawings. We should both have 2 1s electrons. That one is really sad there. There's our 2 1s electrons. And fluorine will bind them tighter. Okay, so this one here is going to be fluorine. Why is the peak higher though? One S. Okay, I'm a little confused by that, but it's because fluorine has a greater nuclear charge than carbon. The 1s peaks for the 2 elements. Why 1s? Why is it so much smaller? I don't know. I don't think it's relevant to the question. Maybe we just had a bigger sample size. I don't know. But the answer is hopefully B. B. And it's because fluorine has a greater nuclear charge than carbon. Yeah. Sorry about that one. I don't know what's up with that one. Okay. Number 12. Please stop me if at any point, you have questions. The first 5 ionization energies within a period are listed to the right. Okay, so what we're going to be looking for is we're going to be looking for a jump in ionization energies, which means we've stopped pulling from the outer shell because we've run out of electrons in the outer shell, and we are now pulling from the inner shell. So if we look for a jump, this is approximately 1,000, right? It's close to 1,000. This is 2,000, this is 3,000. Our first ginormous jump by a factor of 10 is right here, okay, by a factor of about 10. So what that means is that our atom in its outer shell has 1, 2, 3 electrons, 1, 2, 3 electrons that can be removed relatively easily with less energy. The moment those 3 are gone, the next electron we have to remove will be in the next inner shell, which is why it takes so much more energy to remove it, because it is much closer to the nucleus. And it's not just more energy, but a magnitude of energy, a greater magnitude, like an order of magnitude. So that means that we must have something which is in group 13 because it has 3 electrons. So let's go see who's in group 13. That would be boron. It has 3 valence electrons. And if we want to check that, we can go to our periodic table and say boron has 1, 2, 3 valence electrons. I should just have tons of these periodic tables hanging around, then I wouldn't have to erase all the time. That's okay. Okay, so 1, that would be 2s1, 2s2, and then 2s, no, not 2s, 2p1, so it has 3 valence electrons. Okay. Oh, that's not what I wanted. I want notebook. There we go. Come back. Okay, so whenever you've got a series of ionization energies within the same period, different elements within the same period, you're going to look for the big jump. Okay. Ooh, mass spec again here. What have we got? Number 13. The mass spectrum of element X is presented in the diagram above. Based on the spectrum, what can be concluded about element X? Well, its atomic mass is going to be probably somewhere between 90 and 92. Because each of these represents a different mass, and I'm looking here and I'm like, oh, that's got a lot of mass. That's got a lot of percentage. 50% of the atoms are there. We've got maybe 20% here and 20% here, and then, you know, maybe 10% here, and this is 50%. So if I'm just ballparking that, I'm going to go, oh, the atomic mass is going to be not as low as 90, right? It can't be 90 because I've got things above that, but it's going to be higher than 90. And there we are. Mass spec, the peaks don't have anything to do with the oxidation state, okay? And it has nothing to do with the electron sublevels. It is all about the mass. Okay, nobody wanted number 14. Ooh, how exciting. Okay. Anyone changing their mind about number 14 before we zip on past? Okay. Photoelectron spectrum. And of course, remember, we are still seeing here, we have the higher binding energy and we have the lower binding energy on the right. We have the 1s electron, isoelectronic, meaning having the same number of electrons, calcium and argon. Argon is in row 3. And calcium is in row 4. So who has more protons, argon or calcium? Well, calcium, but just double check. Sure, calcium has 20 protons. Argon has 18 protons. Which of the following associates peak X and the justification? Okay, so these are the 1s electrons. And one of these peaks is for calcium and one is for argon. And we want to know the one which has the higher binding energy. And remember, it's going to come down to either the number of shells, but because we have the calcium 2+ ion, and it is isoelectronic, the number of shells is the same, okay? Although it has 20 protons, it only has 18 electrons, just like argon, which has 18 electrons. This would be a different story if we, well, actually, it wouldn't be a different story because we're looking at the 1s. So it really doesn't matter if we've got 20 protons, whoops, 20 protons, and we have 18 protons. If we are dealing with the 1s shell, that's our first shell, do the electrons really care too much about what's happening outside of this area, just right in here? And the answer is no, they don't really. Okay, so it doesn't really matter. What matters is that charge and we have a larger charge for calcium. And so that means that X is going to be the one that has the higher charge, which is going to be calcium. Yes. Okay, very good. So that was number 15, 16. Oh, calcium, because its nucleus has 2 more protons. Remember those completely filled energy levels, the thought that that is somehow especially stable is a bit of a lie that we've been telling you for years and years. So just stay away from that. Argon, because its radius is smaller than the radius of calcium, they want to fool you there into thinking the radius is smaller because it's one period above. The calcium has lost its outer shell, so actually calcium will have a smaller radius, and the nuclear mass has nothing to do with binding energy. So there we are. Based on the ionization energies of element X in the table to the right, which of the following is most likely the empirical formula for an oxide of element X? Once again, we are going to look for the big jump. And if I look, this is like, you know, these are all in the same ballpark, and all of a sudden we've gone up by almost a factor of 10, okay? Sort of. All right, so we've gone up by a huge chunk. So we are looking for something that has 3 electrons in the outer shell, because our 4th electron then would be in an inner shell and more difficult to remove. And if we have 3 electrons in the outer shell, that means it's going to form a 3+ ion, and oxygen, of course, is a 2- ion. So we should end up with CX2O3. Okay. And we don't need to do 17. Ooh, or 18. Ooh. Okay. Number 19. Lewis dot diagrams for CO2 and So2 are given above. The molecular geometry and polarity of the 2 substances are okay. So what is an electron domain? That was a question that was asked earlier. An electron domain, your domain is sort of where you consider your home. So it's like an electron area of living, okay? So when we're talking about electron domains, we are talking about lone pairs. A lone pair is an electron domain. ED, not erectile dysfunction, electron domain. An electron domain. And a bond is an electron domain. And it doesn't matter, single, double, triple, doesn't matter. They are all a single, or they are all one electron domain. Why are they all one electron domain? Because they're all in the same area. If I look at, say, my sulfur over here, where are those 2 bonds? They are both to the right of the sulfur atom. I know that's a 2-dimensional picture, so they aren't really to the right, but you know what I mean. Okay, so they're both in the same area. So if we count up areas where electrons live, for carbon, we have 1 area where electrons live and 2 areas where electrons live. So there are 2 electron domains. If we count it up for sulfur, we have electrons living here, we have electrons living here, and we have electrons living here. There are none living below the sulfur. So this has 3 electron domains. And what do electron domains do to each other? Electron domains repel one another. Domains repel one another. So they're going to try and get as far from one another as possible. If you have two electron domains, the farthest apart they can be is directly opposite each other. So that bond angle is going to be 180 degrees. Okay. However, for sulfur, we have 3 electron domains. So if I just get rid of everything else and I say, I've got my sulfur, I've got an electron domain here that contains that lone pair. In order for the other 2 bonding domains to get as far from everything else as possible, I'm going to have one going out here and one going out here. And these are all going to be approximately 120 degrees. A double bond and a lone pair repel more, so they won't be exactly 120 degrees, but it'll be close-ish. So are the molecular geometries the same? The answer is no. So they are not the same. By the way, what is the shape of this molecule? What is the molecular geometry? This is an easy one. It is linear, yes. Okay, and that is the same as the electron domain geometry. For sulfur, the electron domain geometry is a triangle. What do we call a triangle? Trigonal planar, yes, trigonal planar. Electron domain geometry is trigonal planar or trigonal planar, however you prefer to pronounce it. However, we have this one set which is just a lone pair. We don't actually have something full, like physical kind of sticking off the end of each of these. And so what is the molecular geometry for that? The molecular geometry is bent. Yes. Okay, so they have different, because the lone pairs of S make it a negative end of the dipole. That just sounds really confusing and like it doesn't make sense, which probably means that they're just making stuff up. It is different because sulfur has a greater number of electron domains. Yes, regions of electron density where the electrons live surrounding it than carbon has. Okay, there we go. All right, number 19, number 20. Based on the data above, which of the following statements provides the best prediction for the boiling point of NaCl? So we're comparing NaCl with NaF, right? And so we're comparing fluorine and chlorine. Chlorine is bigger than fluorine. What does that do to the lattice energy of the crystal? If chlorine is bigger than fluorine, do sodium and chlorine bond more tightly or less tightly? Less tightly, because if it's bigger, they can't get as close. Yes? Well, it's not that they can't get as close, it's just they can't be as tight to one another, right? The charges, the center of the charge is, they can't get as close. The center of the charges can't get as close. center of the charges, center of charges, can't get as close. And therefore, we have a lower binding energy. So if it has a lower binding energy, it's going to have a lower boiling point than NaF. Oh, so it has a lower boiling point than NaF because the Coulombic attractions are weaker in NaCl than in NaF. It looks like we have found our answer. Let me double check and see. Yes, it is A. Let's find out why the rest of them are incorrect. NaCl will have a boiling point between that of NaF and MgO. Now, Mg has a larger charge and O has a larger charge. And so it's going to have a larger ionization energy. And so NaCl won't be between the two because both NaF and MgO are going to have a larger lattice energy. NaCl will have a higher boiling point than MgO because the ions are spaced farther apart. That doesn't make sense. I don't think. No, it doesn't, because the charges kind of matter more, I think. Yeah, MgO, because the ions are spaced farther apart than in NaCl. Oh, no. If the ions are spaced farther apart in the NaCl, then it'll mean it'll have a lower boiling point. What am I thinking? Okay, that confused me for a minute, but it does make sense. The ions in NaCl are further apart, and so that would mean that they would have a lower boiling point because they're not as close to one another. And yeah, NaCl will have a higher boiling point than MgO. No, the ions are bigger and they have less charge, so that's just nonsense. Okay, good. Number 21. Which of the following could be the identity of a white crystalline solid? We have a crystalline solid. It melts at 320, so that's relatively high. It does not conduct as a solid. Well, that means it's not a metal, right? Because you know that your metals conduct electricity, so that means it's not copper. But it does conduct electricity in aqueous solution. And if it conducts electricity in aqueous solution, that means it needs to dissociate to form ions. Because if we're conducting electricity, we need something to carry the charge. In copper, it's the electrons that carry the mobile charge. But in an aqueous solution, it's the ions that carry the mobile charge. So you're looking for an ionic compound or an acid. And this is, what kind of a compound is that? It is covalent. So nope, no ions. This one is also covalent to nonmetals. And so nope, it won't carry a charge in aqueous solution. This one will dissolve to form Na plus and OH minus. Now, why can it not conduct electricity as a solid? It's because in solids, the particles don't move. So those particles can't move in a solid. They can only jiggle, yes? But they are free to move when dissolved. Okie dokie. 22 we're going to skip. 23, ooh, binding energy, so exciting. Okay, internuclear distance. Whoa, what happened? Come back here. Internuclear distance basically means I've got an atom here and I've got an atom here and they're bonded together. What is that distance there? Okay, and actually they would be overlapping. So, you know, what is that distance there? Okay. which identifies them as the diatomic molecules X2, Y2, and Z2. So we are looking at H2. Ooh, H2, tiny. H is tiny. Yes, we're looking at its 1s shell overlapping with the other hydrogens, 1s shell. It doesn't have any extra shells. So the internuclear distance is going to be really, really small, okay, because we only have, hydrogen is such a tiny, tiny atom. I don't know why I wrote tiny big, I should have written it small. Therefore, the intranuclear distance is tiny. So that means I'm going to guess that that is going to be, my internuclear distance is big here. So this one is going to be H2. Oh, and by the way, when you're reading this, the internuclear distance is the one where you have the lowest potential energy. So the internuclear distance is the distance with the lowest potential energy. That makes sense, right? Because when the atoms are coming together, we're going to release some potential energy, and we are going to, become lower potential energy. But if you try and push things even closer, like if we took these two hydrogens and tried to push them even closer, the nuclei start getting close to one another, and that causes the potential energy to go back up again. But there's like a happy medium where the electrons, the shared electrons, are attracted to the nuclei most, and that repulsive force hasn't really kicked in yet. And so that's our internuclear distance. Our other two pairs are nitrogen and oxygen. And I know for a fact, and this is just a good thing to know, is that oxygen has a double bond and nitrogen has a triple bond. Okay, that's just a good thing to tuck into your head so that it's easy to access. But if you had to, you could say, okay, oxygen has 6 valence electrons. And so if I go 1, let's see, 2, 4, 6. Oh, and I have 2 of them. So that's going to be 12 valence electrons. So that's 2, 4, 6, 8, 10, 12. You can see we are missing a pair over here. We don't have a full shell yet. So we're going to take a pair and move it into the center. And that gives us our double bond. Nitrogen has 5 valence electrons. And so if we have 2 of them, that's going to be 10 valence electrons. And so now we have nitrogen, 2 for the bond, 2, 4, 6, 8, 10. And we say, oh dear, I'm missing some here, and I am missing some here. So if each nitrogen then donates to the cause, yes. Now each nitrogen has 4 electron pairs around it, 3 bonding pairs and 1 lone pair each. Okay, whereas oxygen has 2 bonding pairs and 2 lone pairs each. Everybody has 8 electrons, a full octet. So what does that have to do with internuclear bonding distance? Well, we have a whole ton more. We have 2 more shared electrons here, 2 more shared electrons than in oxygen. And if we have 2 more shared electrons, that means between my nuclei, instead of having 1, 2, 3, 4 electrons for oxygen, we have my nucleus, and for nitrogen, we have 1, 2, 3, 4, 5, 6 electrons for nitrogen. Whoa, about that. And so because we have a greater greater charge shared here, the pull is going to be stronger. You can think of each of these things pulling upon those nuclei. You can see that's going to be a greater pull than this, which only has 4 things pulling it towards the center. Yes? And why am I ignoring the size of the nitrogen and oxygen atoms? Because they are right beside each other on the periodic table, which means their atomic radii are not going to be hugely dissimilar, not to the same extent of something like hydrogen, which is lacking that shell, so it's going to be a great deal smaller. Okay. So what does that mean? Nitrogen is going to have a stronger pull, so the internuclear distance is going to be smaller because they are pulled more tightly together. So this is going to be nitrogen, and this is going to be oxygen. And so our answer should be, well, let's see, nitrogen is Y, and oxygen is Z. 23 should be A. Yes, it is. That's good. Okay. 24. We have BF3, which is nonpolar, and NF3, which is polar, and we want to know about the Lewis diagram for NF3. All right, so drawing a Lewis diagram, we have N, which has 5 valence electrons, and we have F, we have 3 Fs, which is going to be 3 times, it has 7 valence electrons. Stop me if you want me to tell you how I figured that out. Hopefully you guys know how many valence electrons there are in fluorine. So in group 17, so it has 7, 21 valence electrons. So in total, I've got 5 from nitrogen, 21 from fluorine gives me 26 valence electrons altogether. So now I'm going to put the least electronegative in the center. Also, generally, we put the singleton atom in the center since there's only one nitrogen, it will usually go in the center, the one that there's only one of, and we will put the other 3 atoms surrounding it. Now, we have used up 2, 4, 6. Actually, I taught you guys a different way. So we're going to go, okay, I am just going to fill up everybody until we all have a full valence shell. This guy needs 3 lone pairs to have a full shell. This guy needs 3 lone pairs to have a full shell. And this guy needs 2 lone pairs to have a full shell. And now I'm going to count up my electrons here. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Ha-ha. So that is the correct structure for nitrogen trifluoride, whereas boron has only 3 valence electrons. It's in group 13. And if you remember, boron does not need an octet. It is an exception to the octet rule. And remember, the ones that need a smaller than 8, smaller than 8 electrons, that's going to be the ball. Whoops. So that's going to be beryllium, boron, and aluminum. Okay. So beryllium needs only 2 to be stable. Beryllium, boron and aluminum each need 6 electrons. I meant 4. I meant 4. Beryllium needs 4 electrons to be stable. Boron and aluminum each need 6 electrons to be stable. So if we look at boron, let me attach it to some fluorines. Boron is like, oh, look, I have my 6 electrons. I have 2, 4, 6 electrons. So I don't need more. Don't give me more. Don't do it. And I'm just going to fill up the rest of it. 2, 4, 6, 8, 10, 12, 14, 16, 18. And my bonding pairs, that was 18 plus 6. is 24 electrons, which is how many we have, because if the nitrogen had 26, boron, which has 2 less, will have 24 electrons. So this is a correct structure. So now we are again looking at electron domains. So how many electron domains does boron have? How many areas around boron where electrons live? 3. 1, 2, 3. And how many around nitrogen? 4. 1, 2, 3, 4. So we're going to have a different geometry. And what it means is that if we have 3 electron domains, we are going to arrange those so that the electron domains are as far apart as possible. So once again, we have our trigonal planar arrangement, and this is symmetrical, which means it is non-polar. Okay. If we have nitrogen trifluoride, on the other hand, we have 4 electron domains. What is the electron domain geometry when we have 4 electron domains? What is the electron domain geometry for 4 electron domains? Starts with a T. Next letter is an E. Tetrahedral, okay? It is tetrahedral. Then, if we get into the molecular geometry, where we just look at the actual things attached and not at the lone pair. So what we would really have is we would have nitrogen here. We would have a lone pair kind of sticking up the top. Okay, but it's not an actual physical, doodad. And then below it, we have 1, 2, 3 things sticking out like a tripod. Yes. So this is our little tripod shape here. That is our tetrahedron. But when we discount that lone pair, if we're just looking at the base of the tripod, what shape is the base of a tripod? It's a triangle, yes. And it's a pyramid. So it is trigonal pyramidal, trigonal pyramidal. Okay, so we have our little trigonal pyramidal thing there, and that means that this is asymmetrical. The top part is significantly different than, where's my highlighter? I didn't need to scribble that out. Come on. The top part is significantly different from the bottom part. And so it is asymmetrical. And if it's asymmetrical, it's going to be polar. So how does this relate to our answers here? Unlike BF3, NF3 has non-planar geometry due to an unshared pair of electrons. And that is going to be the answer, and that should be a comma. In NF3, F is joined to N with multiple bonds. That makes no sense. It isn't. NF bonds are polar, whereas BF bonds are non-polar. No, and basically anything bonded with fluorine, which is supremely, like it is the most electronegative, anything bonded with F is going to be polar, other than F bonded with F. NF3 is an ionic compound. That is just nonsense. So even just by process of elimination, if you can eliminate the other three, it has to be D as well. 25. How are we doing? Are we still into doing this? Yes? Okay, cool. If you are not into doing it anymore, you can always take off and just watch the recording. Okay, which of the following diagrams best illustrates how a displacement in an ionic crystal results in cleavage and brittleness? So we're imagining that we're striking this thing with a hammer. Here's my hammer. If I draw a hammer, don't know. Okay, we're not striking it with a hammer, we're striking it with a mallet. Okay, fine. Can't draw a hammer. Brain is gone. Okay, so we're striking this thing with a mallet and we're going to cause a shifting. Yes? And if we shift down like this, what we all of a sudden have is we have negative lined up with negative. Do you see how everybody moved down one? And positive lined up with positive and negative lined up with negative. What do negatives and positives do? They repel. And therefore we get the cleavage, breaking. Cleavage just means a split. Okay, so we get a break. I need to switch pens. This one seems to be a little bit dodgy right now. If we look at our other structures, this is just weird. We've got like a 2+ ion in the middle of nowhere here. Where did that come from? Don't know. Why would hitting it with a hammer cause one of the ions to become 2+? That makes no sense. What kind of a structure are we looking at here? Like what kind of a substance is this one in C? Well, you've got these cations, yes, surrounded by a sea of mobile electrons. And when we hit it with a mallet, because I can't draw a hammer. Okay, when we hit it with a mallet, everybody still stays stuck together because you can see we still have negatives in between all the positives, right? So we're going to have nice bonding interactions there, and that's why this particular one, you might think it's an alloy, but they haven't shown any differences in the atoms themselves, which are shown with the plus charge, right? These all look the same, and the little things in between, it might be hard to see on your copy because you got like a little half-size one. These are just electrons. Okay, so these are all the same. So it is a metal. Okay, so we've got a metal, a metallic bonding. And the fact that we've got these little electrons in between the cations, no matter whether we've hit it or whether we haven't hit it, that means that it's malleable and it won't break. It doesn't have that same sort of repulsive force like we do up here. This last one looks like a long hydrocarbon. Yeah, so this would be like an oil, something like that. Yeah, okay. What did we say the answer was? We said the answer was A. Yeah, okay. Number 26. Lattice energy of a salt is the energy required to separate the ions, or at least it's related to the energy required to separate the ions. For which of the following pairs is that energy the largest? Assume that the distance between the ions in each pair is equal to the sum of the ionic radii. And I don't know 100%. I'm just going to quickly jot down. We have Na and Cl, Na plus, Cl minus. We have Mg2 plus O2 minus. We have Cs plus and Br minus, and we have Ca2 plus and O2 minus. So what we're going to be looking for is we're going to be looking for the things that have the smallest radii, because that's going to bring the charges closer together so they hold on to each other more tightly. And we're also going to be looking for the largest charge. My guess right off the bat is going to be that one, because I've got big charges and I know magnesium and oxygen are near the top of the periodic table. So they have less shells than, say, something like calcium or cesium. So let's just go do a double check. We have our data booklet. Come on. Okay. So if we are comparing sodium and magnesium, magnesium is going to have a 2+ charge, which means it's going to be better at attracting things than sodium, which has a 1+ charge. And they're both in the same row, so their radii are comparable, although magnesium will still be a little, Mg2+ will be smaller than Na2+. If we compare magnesium with calcium, these are both 2+, but magnesium has fewer shells than calcium. So magnesium will be able to get closer to its anion than calcium will. So magnesium is going to bond more tightly with its partner. And finally, cesium. Cesium's just a loser over here. It's only got a 1+ charge, and it is enormous. It's got like 1, 2, 3, 4, 5, 6 shells. It's enormous. So it's really hard to get close to its anion partner. And for our anions, we are looking at chlorine, bromine, and oxygen. So in terms of smallness, oxygen is going to be the smallest because it's only got 2 shells. Okay, whereas chlorine has 3 shells and bromine has 4 shells. So oxygen's the winner on the size front. It's also the winner on the charge front. It has a larger charge. So our winner, ding, 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 is magnesium oxide. Okay, and we go now to, oh, that's what I'm on. What am I doing? No, come back. There we go. Come on. So yeah, it's going to be C, MgO. So always look for the smallest radii and the largest charge for lattice energy. Okay, underwater fireworks. Whew, so we got a whole bunch of reactions. Now, when it says question 20 refers to, that means that this was probably part of a series of questions, and you're going to see this come up later on. But I separated the questions sort of into their categories. So this is all on its lonesome right now. Ooh, hybridization. Hybridization. Hybridization depends upon the number of electron domains. And I know you're going to be really tempted to want to understand this. And we can try to do that a little bit more in depth when we get back. But here's the rule of thumb. If you have 2 electron domains, what it means is that you have an S and a P. 1, 2. Okay. Just go with me here. If you have 3 electron domains, your hybridization is sp2, which means you have 1 S and you have 2, 3 in the P's, okay? Because you've got an S and a P that have been hybridized into 2 sp orbitals. Whereas if we have sp2, we have an s orbital and 2 p orbitals, which have been hybridized into 3 degenerate, same energy, sp2 orbitals. That 2 at the top, that is not a 2 designating how many electrons, it is a 2 designating how many p orbitals are involved in the hybridization. Okay, and what the heck is hybridization? It is a made up thing that we do with orbitals just to kind of explain for our poor little human brains that don't actually really get quantum mechanics. Okay, so we explain that we have 2 degenerate orbitals when we have 2 electron domains, which means that if I've got my atom in the center here, here we go. I have 1 electron domain and I have another electron domain, and they are equivalent to one another. So those are sp. If I have sp2, I have 3 electron domains, okay, that are equivalent to one another. Remember those electron domains, they can be single bonds, they can be double bonds, they can be lone pairs, it doesn't matter. So if you've got 3 things sticking off, you're going to go sp2, okay? Got 1 here, got 2 here, that gives me 3 things sticking off. I know this is not a satisfactory explanation, but it's the fastest way to do it, okay? Ms. and I talk about this all the time. We're like, just believe us. But, you know, people want to understand. I understand wanting to understand. But, you know, it is a made up theory anyway, so maybe understanding it isn't the most important thing. Okay, so now we have S, an s orbital. Come on, right for me, there we go. And we have 3 of the p orbitals, which are going to all become hybridized together. And they hybridize and they form 4 equivalent degenerate sp3 orbitals, which means that we're going to have 4 equivalent electron domains sticking out of our atom in a tetrahedral shape. Okay, so in reaction 3, we go from having C2H2. So C2H2, remember carbon always needs to have, well, almost always needs to have 4 bonds. So if we've got 1, 2 bonds, then it needs to have, maybe I need to switch pens. I'm going to switch pens, see if it's better. So you can see carbon has 2 electron domains. Two areas. And so you go, I need an S and I need a P to provide me with those 2 electron domain areas. Okay, so I have an S and a P, so I'm sp hybridized. So I am looking at either A or B. And we are changing to C2H2Cl2. So we're going to have C2H2Cl2. Okay, and that means that carbon still needs 4 bonds. We've got 1, 2, 3 bonds. So we're going to put a 4th bond here as a double bond in between them. Okay, and now how many electron domains are around carbon? 1, 2, 3 areas. So we need 3 things. So we're going to need an S plus a P plus another P, which means that we have sp2 hybridized. Ooh, I like that way of thinking about it. So if you have 2 electron domains, you need 2 orbitals to hybridize. 2 electron domains, 2 orbitals to hybridize. So you need an s orbital and a p orbital to give you an sp. If you need 3 electron domains, you need 3 orbitals to hybridize 1 s and 2 of the p's, so that's going to give you sp2. If you have 4 electron domains, you need 4 orbitals to hybridize, which means that you need an s and a p and a p and a p, which gives us an sp3 hybridization. Okay, and like I said, hybridization is like not really borne out by serious science, but it's a good enough model for lots of things. So yeah, there we go. Okay, so we changed from SP to SP. Oh, this one had 3 domains, so this is SP2. So we changed from SP to SP2. SP to SP2. 27 is A. And then we get to skip some. Huzzah! Okay, 31. 31. Bond enthalpies. Well, do you remember how I said it is useful to note that oxygen has a double bond? And just kind of stick this in your head. Stop erasing on me, please. And nitrogen has a triple bond. And it's also nice to note that fluorine has a single bond. That makes sense, right? Because oxygen, if we just look at its Lewis dot structure, has, see, now I want you to erase. Oxygen has 2 gaps. Yes, it's got a gap here, and it's got a gap here. So it's generally going to form 2 bonds. Sometimes it doesn't, but most of the time it does. Nitrogen has 5 valence electrons, 1, 2, 3, 4, 5. So it has 3 little gaps. So in general, nitrogen will form 3 bonds. Okay, so we got our 3 bonds there. Oxygen has 2 gaps, so we form 2 bonds. And fluorine, which has 7 valence electrons, 1, 2, 3, 4, 5, 6, 7, has only 1 gap, which means that it can only form 1 bond. Okay, because all the rest of our electrons are just hanging out here. And I'm not going to draw in all the lone pairs, but it is good to know that in terms of bonding, fluorine has 1, oxygen has 2, nitrogen has 3 because of the number of gaps. So if we have more shared electrons, what can we say about the strength of the bond? Oh, can I go over 28 too? For sure. Yep. The bond is stronger, right? Because we've got more charge. And then with fluorine, we've got the least electrons. So we're going to have the weakest bond because we only have 2 shared electrons. So it is going to be the weakest of the 3 bonds. And bond enthalpy is the energy needed to break a bond. Yes? Energy required to break a bond. Sort of. To break a bond. And so who has the largest bond enthalpy? That's going to be the one that's hardest to break. That's going to be nitrogen. Okay, so nitrogen is going to have the highest bond enthalpy, and fluorine is going to have the lowest bond enthalpy. 31 is A. That's good. And we're going to now go back to number 28. If I can find it. Jumping all over the place on me. 28. The potential energy of a system of 2 atoms as a function of their internuclear distance. Oh, that's the one that number 28 needs a diagram. So I'm going to put up a diagram for 28 on the updated one that comes out. You can't do anything without this. Okay. Yeah. Because you don't know where X is on the diagram. So we're not going to do 28 because it needs a diagram and there is no diagram. I will put that up this afternoon after my dentist appointment. Okay, number 32. Which of the following arranges the binary compounds in order of increasing bond polarity? So not molecular polarity, but bond polarity. So we are looking, when we're looking at bond polarity, we're looking at the greatest difference in electronegativity. And remember, electronegativity is the ability to pull bonding electrons towards itself. Ability to pull bonding electrons towards itself. So if you have something with a higher effective nuclear charge, which means you would be going from left to right across the periodic table. So if you have a higher ZF, you're going to have a higher, I'm just going to call it EN for electronegativity, okay? Higher electronegativity. If you have a smaller radius, you also have a higher electronegativity because both of those things affect the Coulombic attraction, that electrostatic force. So the higher the ZF, the stronger the force holding things together, the smaller the radius, the higher the force pulling things in, okay? So we are looking for the difference between carbon, silicon, and sulfur. So let's go look up carbon, silicon, and sulfur and see what we've got. So we have carbon and silicon are in the same group. Carbon and silicon are in the same group, and sulfur is in the same group as silicon. So let's compare carbon and silicon. Who will be more electronegative? Well, they have this essentially the same effective nuclear charge, because remember, effective nuclear charge is equal to the nuclear charge, Z, minus S, the number of shielding electrons. So Z is 6 protons. And S is the number of shielding electrons. And so the number of shielding electrons are the ones that are in the previous shell. So if we look, carbon is in row number 2. So its shielding electrons are in shell number 1. And so the shielding electrons, there's only 2 electrons in shell number 1. So that's going to equal 4. Now, guess what? For silicon, that was for carbon. For silicon, the effective nuclear charge is Z, which is 14, minus the shielding electrons. So that's going to be everything in shell number 1 and shell number 2. So there are 2 electrons in shell number 1, 8 electrons in shell number 2. So that's 10 electrons altogether. So that gives us 4. So when you are in the same group, the effective nuclear charge is essentially the same. It's actually a much more complicated formula, but we don't need to know that. Okay, so we're not worrying about the effective nuclear charge between carbon and silicon. What's the other factor we're looking at? We're looking at the size of the atom, because if an atom is bigger, it is unable to pull the bonding electrons as close to itself. Okay, and so the attractive force will be less. So carbon is more electronegative than silicon. Okay. Sulfur, let's compare sulfur and silicon. Sulfur has the same number of shells, so we're not going to worry too much about its size. It, however, has more protons than silicon. So the effective nuclear charge of sulfur is 16 minus the shielding electrons, 10 equals plus 6. So sulfur has a greater effective nuclear charge, so it is more electronegative than silicon. So going back up. Where did we get to? So carbon has a higher ZEF, so it's going to be, oh my God, now we're looking at hydrogen and chlorine and fluorine. Oh my God, that's a lot of stuff to compare. Okay, I feel like hydrogen and carbon bonds are like carbon and hydrogen have a similar but not identical electronegativity. Hydrogen is sort of off in the corner by itself. So if you just kind of imagine that carbon is approximately equal to hydrogen for its electronegativity. Silicon and chlorine, where are they? Silicon and chlorine are in the same row. Okay. So chlorine is more electronegative than silicon, and it is 3 over. Okay. And we're also looking at sulfur and fluorine. So sulfur and fluorine. Oh, look at that. Sulfur is lower down, so it's got less electronegativity, and it's further to the left, so it also has less electronegativity. So this is going to be our greatest difference in electronegativity because fluorine is the most electronegative. Silicon and chlorine being in the same row will have a difference in electronegativity, but it won't be as dramatic as that between sulfur and fluorine. So this guy here, this combo is going to give us the most polar. This is going to give us the second most polar. And if you remember that carbon and hydrogen are similar-ish, let's actually see what the electronegativity of carbon is. Let me just type that in here. Electronegativity, carbon and hydrogen. Mouse. Carbon is 2.5, hydrogen is 2.1. So yeah, those are really similar values. So yeah, that's going to be the least. So you can just remember, you know, if you've got oils, oils are hydrocarbons, and hydrocarbons tend to be very nonpolar. There's other reasons for that as well. They're also very symmetrical, but in general, carbon and hydrogen. Oh, post attendee Zoom. What happened? Ditch the 40-minute limit. What happened? What? Are we still sharing here? Hello? Let's see. Chat. Oh, we're still sharing. Okay, that's good. I don't know why it says post attendee. That's crazy. Okay, so we're going to go back to here now. Okay. And yeah, so there we are. Come on back. There we are. So CH is going to be the smallest, SiCl4 is going to be second biggest, and SF4 is going to be the greatest. You can kind of just guess that from the fact that fluorine is so electronegative. It's probably always going to be the most involved in the most polar of the bonds, unless it's maybe attached to oxygen. Okay, so yeah, so if you didn't want to think about it as hard as I did, you could just be like fluorine. Fluorine makes things super polar. Yep. Okay. And there's no other option that has fluorine as a component of its greatest. So that would be a quick way of solving that one. 33. Smallest bond angle. Once again, electron domains. Carbon has 4. And they're all bonding domains. There's no lone pairs. So what's the electron domain geometry? Tell yourself. Electron domain geometry is tetrahedral. And if it is tetrahedral, what is the bond angle? (109.5), that is correct. And what is the hybridization? We need 4 things. So I need an S, I need a P, I need a P, I need a P. So that's sp3 hybridized. Okay, good. So we have a 109.5 and all the fluorines are all the same. So that's a solid 109.5. Nitrogen, how many electron domains do we have? How many electron domains around the nitrogen? Four. Yes, we've got a lone pair and we've got 3 bonding pairs. Now, one thing to remember about lone pairs is that they are more repulsive than bonding pairs. So what's going to happen with our tetrahedron is that these guys, instead of being like 1, 2, 3, they're going to be sort of squished a little bit, you know, further down, because they're getting pushed a little bit further. Yes. And so these bond angles are going to be a little bit smaller. So they are going to be less than, that's a terrible picture. It now looks like a spider or something, but we're going to have nitrogen with our thing up here. And we would have 1, 2, 3. And these bond angles are less than 109.5. You don't need to know the actual value. You just need to be able to say it is less. How many electron domains on our sulfur in C? We have 1, 2, 3 electron domains on the sulfur in C. So what that means is that, what's our bond angle? (120), yes. Okay, because it's really going to be S, like that. Okay, so it's 120 degrees. What is the hybridization of sulfur? sp2, yeah, because we need 3 things, an S and a P gives us sp2. By the way, what is the hybridization of the nitrogen in B? Hybridization of the nitrogen in B is sp3 because we need 4 electron domains. And it is tetrahedral in its electron domain geometry. This one you guys couldn't remember earlier. What is the molecular geometry? Or at least you didn't respond to me. You might have remembered it. Molecular geometry is trigonal pyramidal. Yep. Trigonal pyramidal. Okay. All right. And then over here, what is the hybridization of sulfur in D? sp2. Yes, we have 3 electron domains, 1, 2, 3, which means it's sp2. What is the molecular geometry? The electron domain geometry is trigonal planar because we would have sulfur. Like that, but then if we take out the electron domain geometry is trigonal planar, but the molecular geometry is, right for me, bent. Okie dokie. Whew. Atoms in the periodic table. Bonding is done. Let's do chromatography. Okay, chromatography. In paper chromatography, a sample of a pigment is separated into 2 components, X and Y, shown in the figure above. Oh, there's no figure. So number 35 needs a figure. So I'll put a figure with number 35. Because there's no X and Y. Yeah. Yeah. Okay. So number 35, I will have to redo. And now we are on to equilibrium, number 38. How are we feeling? Do we want to keep going until 1? Or do we want to stop now? Wait, do 34, please. Yes. Oh, did I not do 34? Silly me. Until 1 is good? Perfect. Okay, we'll just do until 1. We can talk about actually if you want to do this again next week, we could, or we could just do it once school starts. I don't want to spend too much time in class doing this, so maybe like an after school session or a before school session or a something or other session might order. Think about it while I go over this. 34. Based on the results of the paper chromatography shown, which can be concluded about the dye. It has traveled far. Okay, so it has weak intermolecular forces. That just seems like a really vague statement because there's all kinds of intermolecular forces happening here. There's intermolecular forces between the dye and the dye, between the dye and the solvent, between the dye and the paper. So that's just too vague, right? It doesn't actually specify which kinds. It has a weaker attraction for the stationary phase than it has for the mobile phase. So something that is really attracted to the paper as the water moves, let's say the water moves this far, if the substance is moving and it's attracted to the stationary phase, it's not going to move as far. And the more attracted to the stationary phase, the more time it spends like just sitting still, okay, because it's bonded to the paper. So in order to travel really far, it has to be really attracted to the solvent, the mobile phase, so that it can travel with the solvent rather than being more attracted to the stationary phase, which would mean it would spend more of its time sitting still. So it has a weaker attraction for the stationary phase because it moves quite far up there, yes? Weaker attraction for the stationary phase than it has for the mobile phase. So that's going to be C. Okay. All right. Where are we at now? 38. Are these all like related to something here? Okay, we have this reaction here. So this is a decomposition reaction, which obviously is missing a 5 here. Okay, there should be a 5. Typo. Okay. If the decomposition reaction were to go to completion, the total pressure in the container would be. Okay, so initially we have 1 atmosphere. Okay, so we have 1 atmosphere initially. Actually, I'm going to go over here, PCl5, and let's assume it goes to completion, PCl3, Cl2. So we have an initial, a change, and a final pressure. So initially we have 1 atmosphere, and we have no atmospheres and no atmospheres. And then if it all gets used up, the final pressure due to PCl5 is going to be 0 atmospheres because we've got 0 moles of it left. Well, what did it turn into? I had to have used up 1 atmosphere of pressure. This had to produce 1 mole or 1 atmosphere of pressure. It's a 1-to-1-to-1 ratio. So 1 atmosphere going up by 1 atmosphere. Pressure and moles are directly related. So if you have a 1-to-1-to-1 mole ratio, you also have a 1-to-1-to-1 pressure ratio. And so that's going to be 1 atmosphere and 1 atmosphere, which means that at the end, you will have 2 atmospheres all together, because you went from having, say, 1 mole of gas to having 1 + 1 is 2 moles of gas. And so if you have 2 moles to 1 mole, that's going to be twice the pressure. 38 should be B. 39, which of the following statements about Kp, the equilibrium constant for the reaction, is correct? Okay, so we know that Kp, basically you just write a KEQ expression, but instead of writing concentrations, you write pressures. So we have the pressure of the, what is it, PCl products, or PCl3 and Cl2. PCl3 and the pressure of Cl2 over the pressure of PCl5. How much will we have to know about chromatography for the AP exam? Well, there were 2 questions. So probably not a whole lot. You should maybe be able to calculate an RF value, which we can go over at some point if you would like. Basically, you just need to know that if something travels further, it spends more time in the mobile phase. So if the mobile phase is a polar thing and the stationary phase is non-polar, then the dye or whatever it is would be polar. Whichever one it sticks with most, it's going to have the same polarity, either polar or non-polar. So if it's, yeah, I should really write something down about that because that was really vague, but anyway. Okay, we're going to go back to this one. My brain's getting a little foggy, can you tell? Yeah. So we went from having a total pressure of 1 atmosphere to a total pressure of 1.4 atmospheres. And so again, we're going to do a Rice table, PCl5. In this case, it is an equilibrium, not a going to completion. PCl3, Cl2. And we're starting with 1 atmosphere. We're starting with 0, 0. This is going up by X. This is going up by X. This is going down by, come on, X. So I have 1 minus X. I have X, and I have X. And we know that the total pressure is equal to the pressure of the PCl5 and the pressure of the PCl3 and the pressure of the Cl2, because the total pressure is always equal to the sum of the partial pressures. Now, these are our pressures here: pressure, initial pressure change, pressure at equilibrium. Our equilibrium pressures are 1 minus X. PCl3 is X and PCl2 is X, and the total pressure is 1.40. So now we just do some simple algebra. These 2 cancel out. So we have 1 plus X equals 1.40. And so X is equal to 0.40. All right, does that make sense? So what were we trying to figure out? X is 0.40. We wanted to calculate Kp. Okay, so we have 1 minus 0. No, sorry, this is x squared. So 0.4 squared, because that's both of these are 0.4, both of these are x. And PCl5 is 1 minus x, which is 0.6. And 0.4 squared is 0.16. And so now we have 16 divided by 4 is 4, and 60 divided by 4 is 15. Oh, so I don't even need to do that. Why am I getting excited about finding the value? It's less than 1. So Kp is less than 1. There we go. Did I get it right? 39. B. Hey. Woo. Okay. 42. And I think this will be our last question. 42, it is observed that the reaction between KCl and its elements goes essentially to completion. Which of the following statements is thermodynamically favorability of the reactants? So our heat term is here. The reaction is favorable. They react directly to form that. It goes to completion. So this thing goes to completion. So that means it's favored by enthalpy. And is it favored by entropy? I got a gas over here. So the S is favored over on this side. S is higher here, and S is lower here, and we want to have a high S. So S favors the reactants, H favors the products. The reaction is favorable because it goes to completion, so it has to be favorable. And heat says it goes forward, but entropy says it goes backwards, so it is driven by enthalpy only. Okay. Do we want to do this again next Friday at 11? Or shall we just wait till school? Nobody cares. Okay, so I will see you at school then. Excellent. So have a great rest of the break. I will, yeah, no, nothing new. Okay, have a great rest of the break. Yeah, that's all. My brain has stopped, so I'm just gonna say goodbye now. Thank you for showing up, all 6 of you, except for maybe it's only 5 because 1 is me.